Okay, so here is the problem from strength of materials. Basically, a simply supported beam is given, which is loaded as shown in the figure, where you at the center it has the maximum intensity of the load, and the maximum intensity is given as 1 kilonewton per meter. And whereas otherwise it's kind of a triangular loading, right, where it is zero at the ends and peaking at the middle of the beam. So what is asked is the maximum bending moment that occurs in this beam. Okay, so before doing that, what we do is we'll just get the reactions first. Okay, so you have a loading like this. Okay, so simply supported beam, so we'll have both vertical reactions at A and B, and there's a horizontal reaction at the left end, but that is zero because you don't have any horizontal loading. So this is A and this is B. Okay, and how do you, when you are taking the entire free body diagram of the beam, how do you replace a distributed loading? A distributed loading, the value is, the magnitude is nothing but, magnitude of the distributed loading is area of the triangle, area of the loading curve, loading diagram. So area of the loading diagram is nothing but, from this we can say it's triangle, so half base into height. Base is L, height is W, so WL by 4, and it should be replaced at the centroid of the loading, at the centroid of the loading. Remember, it's centroid of the loading diagram where you got to replace. Now from this you can just simply say that because it's symmetric, you have half triangle this side and half triangle that side, so it has to be replaced at the center. The center of the loading diagram is this, so WL by 2 is at the center. So obviously from this you can say that A and B has to support equally. So A is half of WL by 2, which is WL by 4, and the reaction at B is WL by 4. I mean, this is a simple thing. Otherwise what you can do is you have to just balance vertically. A plus B is WL by 2, and you have to take a moment about any point and then just summation of moment is equal to 0. At the end you are going to get the same thing because looking at the loading diagram, it's symmetric, so WL by 4, WL by 4. So once you get that, now basic thing you should understand is that, so we got the reactions. Now basic thing you have to understand is that when you have a symmetric loading and you have a simply supported beam, the maximum bending moment you expect is at the center. Like if you remember this case, when you have a simply supported beam and you have a UDL, okay, which is again asymmetric in loading. So where did you expect, in the bending moment diagram, the maximum bending is, so bending moment diagram for this case was like this. It's a parabola with a curve with the peaking at the center. So the point here is that it's a simply supported beam and there was a UDL which was again symmetric. So when at this symmetric case, when you have a constant UDL acting, you got at the center the maximum. This is how the bending moment diagram for this case look like. Now for our case, obviously you don't have a UDL, but you have a loading such that which is peaking at the middle. So obviously even in the case when you have a constant UDL acting throughout the beam, you get the bending moment diagram at the center. So in this case you will expect, in fact it is the case that you expect you get the bending moment at the center. So what we do is we take a section and take the right side of the beam, and then we can get the bending moment. So what we do is we take a section at the middle, and the right side of the body we consider. So what are the forces on the right side? So it's WL by 4, and the loading is like this. This is how the loading is, and you have the shear force diagram. So at this section obviously you will have a bending moment which is like this, and you have a shear force which we assume that it's V. So we need to find out M at the center, and at the center you know that bending moment is maximum, so that M we need to find out. So how do I replace this? So how do I replace triangle loading? The same thing, the triangle loading, the area is nothing but the magnitude of this of triangle loading is the area, which is nothing but this is W and this is L by 2, half of the beam. Okay, so W half base, let's do it here, half, base is L by 2 and height is W. So WL by 4 is the magnitude of the right side UDL, WL by 4, and where you have to replace, you have to replace at centroid. The centroid is somewhere here. Okay, this is the place where you have to replace, and the centroid, the length of the centroid is 1/3 from the maximum intensity low end. So that's how you have to replace. So 1/3 of the total, the maximum intensity, so L by 6. So it's like this. Let me summarize here. When you have a triangle loading, how do you replace this UDL? You replace with the magnitude. Magnitude is area of the triangle, which we got as WL by 4, and you have to replace at 1/3 of the triangle length and 1/3 from the maximum end. So 1/3 of the length of the triangle, that is 1/3 of L by 2, which is L by 6. So now this UDL will be acting, the value is WL by 4 and it is acting at L by 6. L by 6, and this is nothing but the reaction WL by 4, which is L by 2, and this is moment, and the shear force is V. So we need to get this moment. So what we do is we take a moment about this center. So moment about center has to be 0. You take any part of the beam, if it is in equilibrium, moment about any point has to be 0. So we have taken the right side section. Forces should balance, the moment should balance, the moment about C has to be 0. Moment should balance about any point, so we take at C. So when we take at C, because why we are taking at C? Because we don't know the shear force there, and the shear force gets eliminated if I take moment at C. Okay, so now WL, so let's see the reaction. So WL by 4 produces a clockwise moment, so we take clockwise positive. And okay, so WL by 4 into L by 6 clockwise, WL by 4 produces anti-clockwise, so WL by 4 into this total length, the total length is L by 2, and M is clockwise, so plus M is equal to 0. So what is M now? M we have to, because at C also there is a moment acting, so that moment will come. V will not come because it's a force passing through C, but the moment passing through C you have to take. That's what M we have taken. So this is WL square by 24, and this is WL square by 8, plus M is equal to 0. So what does this mean? M is equal to WL square by 8 minus WL square by 24, which is nothing but 24 minus 8 is 16 by 8. Okay, so let's do it here. So the value which we get is 16 by 8 into 24 WL square. So that is WL square by 12. Okay, so let's substitute W. So WL square by 12 is the answer. So let's go to the top. Okay, so we get the maximum bending moment is WL square by 12. Now let's substitute the value, which is 1 kilonewton, so it is 10 power 3. Length is 10 meters, so 10/100 by 12. So this value, if we calculate, we get 8,333 Newton meter. So that is the answer, 8,333 Newton meter. Thank you.